Welcome to this online Maths Open Day talk. So in the next 20 minutes, I would like to give you a taste of the beautiful mathematical construction that we have behind our current understanding of elementary particles. As a theoretical physicist, I stretch my mind between fundamental particles smaller than an atom to things as big as the universe. In the image on top here, you start from a sandcastle and you start looking at the smallest constituents from the crystals that make up the sun, 10 to the minus 7 centimeter, to the atom that are about 10 to the minus 8 centimeter. Then you go to the nucleus inside the atom that is about 4 orders of magnitude smaller than the atom itself. And finally, to the quarks that make up protons and neutrons that are about smaller than 10 to the minus 16 centimeters. So how does it relate to the universe? Clearly, this is because at the very beginning of the universe, after the Big Bang, particles were created in their elementary state, and only later they assembled to form atoms and molecules. But what is the guiding principle in this adventure of going from the tiniest to the biggest? Mathematics is truly our compass. In the rest of the talk, I'd like to give you 3 examples of that. So first of all, I will talk about the symmetries that are behind the standard model of particle physics. And to get there, I will go into steps, starting from the symmetries in the classical sense as formulated by Emmy Noether, then going into global symmetries, and finally into the modern symmetries that guide our building of theoretical physics theories. And then I will walk you through the adventure of the discovery of the Higgs boson, and finally, what are the questions that open up as a result of the discovery of the Higgs boson. So let me start from the standard model of particle physics. Here you can see on the right-hand side of the slide, you can see a nice image of the main building blocks of matter. So all the particles, the fundamental building blocks of all particles we know, that are the quarks and the leptons that come into 3 families. And then on the right-hand side, you see the 4 bosons that mediate the electromagnetic and nuclear interaction among these matter particles. And in the middle, you see the Higgs boson, that is a fundamental spin-zero scalar particle that has to do with the masses of all particles we see and with some of their important interaction. What is amazing is that the vast amount of phenomena that are described by the standard model can be written with a very simple mathematical expression, that is the Lagrangian of the standard model, that you see on the left-hand side can be written on a mug. Let's look into all the particles you've seen in the previous slide in here. And here you can see a timeline of when these particles have been discovered and whether before being discovered they've been either theorized or made up to explain some experimental phenomenon. So what you notice is that most of the particles were somehow thought of before their discovery, apart from the muon and the tau that were really surprised, so that nobody could think of them. They were discovered experimentally. And of these, you can see that some were made up to explain phenomena. But the ones that are circled in green here were really theorized by starting from some basic theoretical principle without having any experimental hint. Let me try to guide you through that to see what can be this theoretical input that make us think of the existence of a particle before this has been discovered. We have to start from the concept of symmetry, because this is really the guiding principle that I try to make you understand. So what is a symmetry? So by symmetry, as physicists, we mean the invariance of the laws of nature under some transformation. For example, that if I drop this pen now, and if I drop the pen in 10 minutes, the same phenomenon will happen. Or if I drop the pen here and you drop the pen from your home where you're listening now, the same phenomenon will happen. So this is the concept of symmetry. And Emmy Noether made this amazing mathematical discovery that whenever we have a global symmetry in the mathematical expression that describes a certain phenomenon, this symmetry yields the conservation of some physics quantities. For example, what I just mentioned before, so the fact that if I drop a pen now, or if you drop a pen now from your home, the same physics happens. This implies the conservation of the momentum. Or the fact that if I do this experiment now or in 10 minutes and the same thing will happen, this implies the energy conservation. So really, without going into details, what the main message from here is that really is not the dynamic of physics law that defines the symmetry, rather it is the symmetry that defines the dynamics law of physics. Let me give you another example. This happens about 50 years later. At some point, towards the end of the 50s, people were happy with the proton and the neutron being elementary particles. Now we know they are not. We know they're made up of quarks, but at the time people did not know. And people thought, okay, fine, we have the electrons, the photons, and proton and neutrons, and so on. And these are our elementary particles, until with the beginning of modern colliders, more and more particles, they were strict relatives with the protons and the neutrons, but not like them, so they were heavier, they were all created. So at some point, as you can see here, the number of supposedly elementary particles was rising a lot. So there were many more particles. And immediately, physicists got alarmed. So they thought an explanation of the matter must be simpler than that. We cannot have so many elementary particles. And Gell-Mann, who got the Nobel Prize for this idea in 1969, came up with an amazing idea of using a symmetry that we call the global flavor symmetry to organize all these relatives of protons and neutrons, which we call hadrons. So to organize all the hadrons observed in terms of smaller constituents, elementary constituents called quarks. And this was the purely theoretical birth of the idea of quarks. Now let's go to a concept of symmetry, which is really the one that guides our particle physics, so modern theoretical particle physicists now, which is the idea of local gauge symmetries. That's really complicated. I'm not demanding you to understand it now, but at least to give you a flavor of what it is. So the local gauge symmetries, what do I mean by that? So we have this function of space and time, which we call field. Each field is associated with a particle, so one of the particles that I showed you before. We can start from a given kind of particle and we impose that the laws of nature are invariant under a local gauge symmetry. So under a transformation of the fields that involves a field A that depends on space-time coordinates. So I ask that whatever is my physics law doesn't change when I send phi into e to the I a phi, where A is a local transformation, so depends on the space-time coordinates. If we impose such a symmetry, for example, take quantum electrodynamics. Feynman was the father of it. So if we impose gauge invariant upon a given symmetry group onto the electrons, at that point we are requiring and we are predicting the existence of a zero mass particle that mediates the force between electrons, so that mediates the electromagnetic force. So the symmetry dictates the interaction. So this is this mathematical formulation of a free electron that is moving around into space-time. If we impose that the field psi that you can see here is invariant under the transformation you see on the top of the page, then we have to add this other term into the Lagrange. That same as a Feynman diagram is really the interaction of two electrons via the exchange of a photon. And at that point, because we now have predicted the existence of the photon, we can add the term into this physics law for the propagation of a free photon. I find this amazing because this was really the principle that led us to build the standard model as I showed you in the previous slide. In particular, imposing the local gauge symmetry of this geometric group SU3 color, we are predicting the existence of 8 particles called gluons, so the G that you can see here among the forces, that mediate the strong nuclear interaction. Imposing the local gauge symmetry of this other geometrical group called SU2 left, we foresee the existence of 3 gauge bosons, this W and Z, that mediate the weak nuclear interaction. And doing what I showed you before, so imposing this translational space-time dependent symmetry of the electron field, we are predicting the existence of a photon that mediates electromagnetic interaction. I find this totally mind-blowing. And something that is even more complicated, so I'd only mention it, I don't really demand you to understand it, is that the Higgs boson is the particle that is predicted when this global gauge symmetry is broken to a smaller symmetry. There is a mechanism, there is a mathematical mechanism that tells you that when you break symmetry and go to a smaller symmetry group, then you predict the existence of other particles. And the Higgs boson is exactly this particle. Let me now tell you the story, because it's quite recent, it happened in 2012, of the discovery of the Higgs boson. Because the breaking of symmetry mechanism was invented in the 60s, but it was only nearly 50 years later that this mechanism was observed. So what does it mean that people discovered the Higgs boson? What does it mean that a particle like the Higgs was discovered? So you don't see it like that, so you really need to create it by smashing particles against each other at a huge velocity. And the smaller you want to see, the faster you have to smash the 2 particles against each other. And this is the concept behind the Large Hadron Collider that you all know. Is this 27 kilometers circle in Geneva underneath the Swiss Franc border. Two beams of protons are accelerated at almost the speed of light. And this energy state, this created after this collision, is really similar in terms of energy to that shortly after the Big Bang. That's why it's called a Big Bang machine. Around the circle here, there are four big detectors that are like big cameras that take pictures of what happened when protons smash against each other. For example, this is Atlas, one of these four detectors, one of these four cameras, and you see that it's huge. So you can see how big it is compared to the man in there. And each layer takes special picture of some special particles. Let me see, I show you what happens inside. So you can see the two beams of protons are accelerated by speeding them up into larger and larger rings until they reach almost the speed of light. At that point, they are injected into the ring into opposite direction, and the protons are made collide into these four interaction points. As you can see here, the protons are not elementary particles, rather they are made of quarks. And look, when they approach the detector, so when they approach one of these big cameras, they are deflected slightly so that they smash exactly in the middle of the detector. And as you can see here, out of two tiny protons, you get a huge amount of new particles. And taking billions of pictures like that each second, we reconstruct what happens when two protons die into some other particles. So what you have just seen in this simulation is really Einstein's relativity at work, because when two protons smash against each other, energy, at the very high energy turns into matter. So it's as if out of two protons of mass 1 in some unit, you get a mass that is larger than 300, because they go so fast that the energy transforms into mass. And after almost 5 years of running, finally there was a big announcement. It was on all the newspaper on the 4th of July 2012, that this particle that was the last one to have been predicted but not yet found, has been finally detected. And I show you the video of what happened at CERN.
Now the grand combination. The channels that you have seen before, together with the other channels from the 2011 results.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that has happened in my lifetime.
So as you can see, these were Professor Higgs and Angler, who got the Nobel Prize for the discovery of the particle that they had predicted 50 years before. But what was shown there at CERN on that day was a bump. So what does it mean? So that was the data collection. So basically, the physicists at CERN had collected billions and billions of images of two photons in the final state. So two powerful rays of light coming out of the collision of two protons. These two rays of light can be produced in many ways. X is all possible ways that do not involve the Higgs boson, in which two rays of light that have a certain energy can be created. So people started to collect this data 2011. As you can see, as time goes, more and more pictures are taken. And you can see a line that is compatible with this blue line. So as if the Higgs boson was not there. So the photon have been created simply by other mechanisms. But on top of the blue line, you can see clearly and statistically that there is a bump, a red bump into this line. And this means that there is something more. So there is something more that they can create two photons at that given energy. And that something more was exactly the particle predicted by thinking of the breaking of the gauge symmetry by Professor Higgs and Professor Angler. So discovering a particle means really to look at the statistical distribution of these events that been taken picture of at the Large Hadron Collider. So now one could think, is that the end of the story? So we are all excited in 2012 because this latest particle that was predicted by the standard model has finally been found. Is that the end of the story? Should we all change job? Clearly the answer is not, because each discovery opens up a whole new universe of questions. In fact, now what we're all working on as theorists is to predict and to find, as experimentalists, new physics, something beyond what we know. For example, what are the fundamental questions that we need to answer? One question is, what is the origin of the matter-antimatter asymmetry into the universe? So why the matter and antimatter that was created at the beginning after the Big Bang has not completely annihilated, but rather matter as one to create all the planets and galaxies and everything we see now? Or what is dark matter and dark energy made of? Because everything I told you is about the regular matter. That is this 5% you see in this diagram of the whole universe. Actually, 95% of the universe is made of things that we do not know what they are, but we hope that they can be produced at the LHC and we can find them in the same way in which we found the Higgs boson. Or how does gravity fit into the picture? So everything I told you is about electromagnetic and nuclear interaction, but we know that particles interact also via gravitational interaction. So these are some of the fundamental questions that we are trying to answer to, using really the symmetry as a guiding principle. And to do that, we don't only need ideas based on symmetry, we need also to verify this idea. So we need really to make precise theoretical predictions, because using what we know, if we want to find the background upon which something that we do not know, some new particle or new interaction, can be detected. So that's a very fascinating challenge that we are all pursuing with all our imagination and our stamina. And I think it's really an amazing adventure. So with about 1 billion events per second and more of 10 years of data taking from now on, and so many data still to analyze, we are definitely sure that surprising discovery might just be around the corner. So just stay tuned, and thank you very much for your attention.